Hello, everybody. Welcome, and thank you for being here. My name is Colton Dillion. I'm the CEO at PostQuant Labs, and we're building Quip Network, the worldwide quantum computer which will solve jobs which no other platform in the world will be able to solve. A little bit about me. I'm a crypto native. I've been in the space since 2017. Did degen token on Base last year. Worked on multi-party computation wallets, and did fintech back in 2012. My co-founder, Rick Carback, he was one of the co-founders at XX Network, did the first post-quantum double ratchet protocol, which is the protocol that Signal uses if you use the Signal app, and worked in cybersecurity with Charles Stark Draper Labs. Formerly, I was also doing electromechanical engineering for Intel and Nike's wearables division, but ended up in finance after grad school, and it's really good to be back in quantum computing. A lot of you are probably here today because you're worried about quantum computers affecting the cryptocurrency ecosystem. You may have seen back in 2021 that Craig Gidney published a paper that said you could break RSA 2048 as long as you had 20 million noisy qubits. Last year, he published a paper that said you could break RSA 2048 with 1 million noisy qubits. So over 4 years, we had a 20x factor improvement in how many physical qubits would be required to break RSA 2048. Last week, there was another group, Iceberg Quantum, that published a paper saying that they had reduced this to 100,000 physical qubits in just 1 year. And this doesn't just affect RSA 2048, it also affects elliptic curve cryptography. So as you, I'm sure, might be aware, ECC 256 is what we use in a lot of our cryptocurrency networks today, and quantum computers can just as easily crack these keys with the same number of physical qubits. So how close are we to actually getting there? Well, Atom Computing has a 2,000 qubit computer to do gate operations on. If you use quantum annealing, which is a different type of quantum computing, D-Wave features 10,000 qubit computers at their state-of-the-art laboratory. And so we have multiple efforts occurring across Google, across Microsoft, Amazon, IBM, all trying to increase these number of qubits and making progress every year. In addition to these algorithmic improvements and these manufacturing improvements, we also have research improvements in terms of having better error correction. So your qubits are more likely to get a correct answer and you don't have to go back and try the whole computation again. But what I'm here to tell you today is that we've already solved this problem on Ethereum. You can actually use quantum-resistant wallets today, and for the vast majority of cases, you can just use these quantum-resistant wallets. And so the technology that is used to protect against quantum computers is commodity. You can literally pull algorithms off the shelf that we believe are resistant to quantum computers today. And so what I really want to talk to you about is the opportunity that quantum computers represent. Because you have all of this excess compute capacity that quantum computers enable you to solve highly connected problems, you can essentially apply them to many other domains, like creating molecules, simulating different materials in the lab, creating drug candidates, and getting more certainty about the behaviors of those drug candidates before you invest a lot of money in a trial. Doing logistical optimization, trying to create better supply chains, more efficient manufacturing processes. All of these things are very high combinatorial spaces that quantum computers can help us to analyze more efficiently. Doing weather simulation, starting to think about problems that it would literally take longer than the lifetime of the universe to analyze on a classical computer, you'll be able to do in hours or days on a quantum computer. So why do we get that? What is quantum computing? The fact is that it's lateral computing. In the same way that we talk about lateral thinking, you're trying to use these properties of quantum mechanics, of having probabilistically entangled systems, where if you have one event on one system, then that affects the likelihood of the outcome on another system. If you have interference, where the states of two systems can cancel out, and the symmetries around those systems can essentially reduce the exploratory space that you need to crawl, you can get huge performance improvements by using quantum computers instead of a classical computing cluster. And so in reality, we are saying that all of these problems that were not solvable on a classical cluster will be solvable on a quantum computer. And we're just starting to hit that inflection point where quantum computers do have applications that they can either get time to solution, solution quality, or energy cost advantages over existing computers on problems that matter to industrial actors. The problem is that right now, each of these machines can cost up to $20 million. And so it's not exactly easy to get access to them. They're very finicky machines. They have to be isolated. They have to be kept near absolute zero temperature in many cases. And so if you don't have full utilization of the machine, you're just wasting energy. One of the benefits of quantum computing is that you can try multiple times and you can build a probability distribution of the correct answer to your problem. And so looking at all these factors, it seems like there's something we're very familiar with in cryptocurrency that would be a really good fit for getting a large network of quantum computers to solve problems together. And that's useful proof of work. So that's what we do, is we build a useful proof of work that quantum computers that can't be turned off can operate on when they don't have anything else to do. We essentially sell the excess time on these machines in order to build a large probability distribution and to be able to select the best answers out and get you a more efficient answer faster with less energy. So we're kind of like Hotel Tonight or Airbnb for the excess time on a quantum computer. In the same way that if you don't fill up your hotel or your house and you can put that excess capacity on a marketplace, if you own a quantum computer and you're not using it all the time, which most people are not, then you can at least put that capacity on a decentralized marketplace. One other benefit is that you can actually connect these quantum computers together via entanglement, and you can make the states of each of these machines dependent on parts of the state on other machines. And it turns out that when you do this, you can essentially get extra qubits out of your system. So as an example here, I'm showing that we have 3 2-qubit systems, and when you combine the 2 qubit systems together, if the second 2 systems are reliant on the first system, then you essentially have a 6-qubit system. But then, if you take the tensor product with the third system, now you have an 8-qubit system, where before you only actually had 6 qubits on your machine. And so by connecting these computers together, you will be able to solve bigger, hairier, more dense problems that are even more difficult to solve. And so our belief is that in the future, when you want to solve the hardest problems that humanity knows how to even ask the question, you will have to connect every quantum computer together. You will have to build a worldwide network that is one giant quantum computer. So that's what we're building. We build the infrastructure for that quantum internet and for that worldwide quantum computer to make sure that you can share work, you can ensure that the people who participate get paid, and that bad actors can be punished. Quantum computing is a defensively, strategically sensitive technology. Because people can use it to break cryptography, we don't want just anyone using it. And there will be many actors in a decentralized network who want to deny service to other actors in the network, who want to spam the network, who want to drop packets. If they're participating in an entangled program, they may measure their program early, which will affect the outcome of the program on other machines. So how do you catch this work, and how do you punish it? And that's a lot of the research that we do here at PostQuant Labs. One of the things that we're focused on is that there aren't many quantum computers in the world right now. There are maybe 200 in the world total that people are operating on different labs. And so if you create a decentralized network, there's not really a lot of decentralization there. So how do you actually create that confidence in the trustlessness of that network? Well, we are focused on proofs of work that can be verified and validated by classical computers in the early days. And once these computers grow, once there's a larger network of quantum computers, then you can move into complexity classes that can only be validated or only be executed by quantum computers. So you will be able to download a node, and you will be able to compete or verify the work of the quantum computers and get paid for that service. And you'll be able to exchange the compute on your computer for the compute on a quantum computer. The way we're building this network, we want you to be able to focus on the parts of the problem that you care about, right? If you are not a quantum developer, you don't need to learn exactly how quantum computing works. You don't need to learn about complex analysis and tensor products. You should be able to focus on the things that you're good at. And so we have separated out the different layers of this service so that the quantum algorithm designers can focus on the useful proofs of work and the most optimal ways to execute those proofs of work to make sure that they compile to the different types of quantum computer targets. And then there are essentially transformation smart contracts that take your industrial data and transform them for the useful proof of work. And it may be that in some situations, going through the proof of work doesn't make sense. You might have a more efficient algorithm where you can act directly on the data and get an answer for that end consumer, and that's great. We think that the chain should be a benchmark, a living benchmark of every possible application and every possible processor to see which platforms actually perform on the problems that matter to industrial actors. So who are these ecosystem participants? Well, it's all the largest quantum computing manufacturers in the world: D-Wave, IBM, IonQ, Quantinuum, Quera, etc. In addition, you have classical operators, so everyone who's already been operating in the cryptocurrency space for the last decade, they can participate in this network. They can use the same hardware to validate that the quantum computers are really doing valid work. And there may be other actors who want to contribute ASICs or FPGAs for certain useful proofs of work. We also have compute consumers, who are these people who are getting use out of the quantum computers. Groups like State Street, who are using quantum computers to do financial analysis, risk management, to find arbitrage. These are all applications that quantum computers can outperform on. Six Systems is a group that we're working with where they produce factory designs. So they try and optimize the space of factory designs to produce certain chemicals, either reducing inputs or increasing yields or optimizing the cost of the CapEx at some penalty on the OpEx. Or even prime intellect. AI is one of the key applications for quantum. You can actually do more efficient learning, training, inference on small models than you can on large clusters of GPUs, but currently we're limited by the size of the quantum computers. But you can save up to 300 times as much energy compared to a cluster of 1,000 H100 GPUs based on our early testing. After we build these useful proofs of work, we do envision that quantum miners will begin to pool together and to actually entangle their processors together. If you know ARPANET from 1969, it started with 4 universities. It was UC Berkeley, UCLA, Stanford, and University of Utah. And that was the beginning of the internet. And so we believe the beginning of the quantum internet is right here in Colorado, Wyoming, and New Mexico. I open it up to questions, and I thank you all for your time. I do want to mention as well that we have a quantum-resistant swap protocol. You will not have to migrate your funds to our chain. You can actually interact with our chain directly with liquidity from these quantum-resistant wallets on your existing chains. So this is a demo. The first person to claim it can get $20. If you talk to my team, there's many more holding $5 each. And so find the Quip Network team and test out this product. We'd love to work with you. Come check out quip.network. Are there any questions?
Yeah, we do have to move on. So if you have